Okay. Thanks for the introduction, and thanks to the organizers for this amazing conference and for letting me talk here. So basically I'd like to talk about my research project on SUN structures with torsion. And so first, I'm going to give the definition of what an SUN structure is. So basically, I start with a smooth manifold of dimension 2m. And I have several data on it. The first one is J, which will be an almost complex structure. And I really insist on the fact that my complex structure is only almost. Then I have a 2 form, little omega, which is 1, 1 with respect to this almost complex structure, and which is J compatible. Meaning that you have a Riemannian matrix induced by those two. And finally, I have what I call a complex volume form, and I denote big omega. Which is an N0 form and satisfies a normalized condition, which is the following. So I take its wedge with its conjugate, and it's just a constant times the Riemannian volume form. Okay, so this is the definition of an SUN structure in general. I'd like to insist on the fact that my J is almost complex. So the main difference between this and the complex word is the following. So imagine I pick a PQ form, okay, and I take its differential. In the complex word, usually you have a P plus 1 Q component plus a PQ plus 1 component. But it turns out that in almost complex word, it's not longer true. You may have a P plus 2 Q minus 1 component and a P minus 1 Q plus 2 component. So that's what happens. And so with that said, I can give you the notion of torsion of an SUN structure that appears in the title. Somehow it will measure the integrability of my structure here. So torsion. So this was first studied by Gray and Hervola in 1980. And so basically what you're going to do is to look at the differential of these two forms, okay? Because you have this kind of decomposition. So let's write it down. So you have something like that. Let's some conjugate terms. And you have for the complex volume form, you have something like that. So there are many different terms here. You have the WI. The WI are known as the torsion classes of my structure, and each of them has a particular form. This one is an N-3 0 form. This denotes the contraction with respect to the Riemannian matrix on my manifold. This is a 1-0 form. This one is a 2-1 form and primitive. Okay, this W2 is N-2-1 primitive 2. And W5 is 1-0. And so each one of these torsion classes encodes some kind of special feature on your manifold. For example, if you want your 2 form to be closed, you will ask W1 and W4 and W3 to be 0. And the most well-known example of this kind of structure is the Calabi-Yau structures, in which all the torsion classes vanish. Okay. And so this is interesting for physicists, physics purposes. mainly to relate to the string theory, where usually physicists are looking for a Calabi-Yau manifold of dimension 3. But it turned out for their purpose, they need something a little bit weaker, which I defined. And is known as LT structure. So LT stands for the name of two physicists, Lust and Simplice. And basically they are defined as SUN structures where we require W3, W4, and W5 to vanish. Okay, and that's the kind of structure I'm interested in and I'd like to study. And so to do that, we'll present you now a construction of SUN structures in general, because if I want to study these LT structures, I need somehow to have something explicit so I can compute the torsion with this kind of formula. Okay, so what is the construction? So I'll give you the theorem. So I start with, let's say, xn plus 1. N plus 1 is for the complex dimension. With, say, little omega x and omega x. I assume it is scalar. And this omega x and omega big omega x is an SUN plus 1 structure. Okay, and now also assume I have a Hamiltonian action of the cycle on x. So Hamiltonian plus I will ask also to be holomorphic. Okay, and let's denote y a symplectic quotient using the momentum map given by this Hamiltonian action. Quotient. Now here comes the main assumption of this theorem. Assume there exists a twist form, so I'm going to define it in a minute. I call alpha, and then I set two forms. Big omega, which is going to be alpha, the conjugate of alpha, wedged with something like that, where V is any vector field induced by the action of S1 on X. Little omega, which is the following. Okay, and this I claim that it defines an SUN structure on the quotient Y. Okay. Y. Okay, so let me explain what a twist form is, because it's the main assumption of this theorem. So to see what this is, let me start by taking V as the V in this statement, a vector field induced by the action. Okay, and so I can look at the Lie derivative of my volume form with respect to this action. Okay, and this, by assumption, it turns out there is a multiple of this of my complex volume form. Okay, and this Q here, I'm going to call that the charge of the complex volume form. So it really depends on the action here. Okay, and so a twist form is so it is a nowhere vanishing really important condition. 1-0 form, okay, which is horizontal. Horizontal means that it annihilates the vector fields induced by the action. And it has a charge, like given like that, whose charge is precisely half of the charge of my form here. Okay. And so with all this ingredient, I can cook up some Gaussian structure on Y. So the way I see this alpha is the following. So because it is a nowhere vanishing 1-0 form, I can see it as a form that gives me a direction of the fiber of my holomorphic tangent bundle, okay? And here, notice that I'm taking its conjugate, okay? So basically what I'm doing is I'm reversing this direction in my fiber. So somehow you must think that this alpha, which is 1-0 with respect to the original complex structure here, becomes 0-1. That's the trick that makes this thing work. Another remark about this theorem, which is that I put here an S1 action, so that you can replace with any compact torus action, actually. And there's even a more general version where here I only took one twist form, but we could imagine I'll take several twist forms which satisfy an orthogonal condition, whatever that means. And so I can still construct something like that. Okay. Yeah. Yeah. Oh, this is the contraction with respect to the metric. So you can identify the 1-0 forms with vector fields. This is what. Here is a contraction too with yeah, several notation. Yeah. Thank you. Okay. And so now I'd like to present you an application of this theorem in the case of Calabi cones that that Evelyn told about yesterday. So let me recall briefly the setup. So I start with Y, which is Fano-Kähler-Einstein manifold. So Fano means that the anti-canonical bundle is ample. Kähler-Einstein, like we seen in the talk earlier, it means that the Ricci curvature is just proportional to the metric. Okay, and with this Fano-Kähler-Einstein manifold, I have, let's say, of complex dimension n. I can associate a Calabi cone, which is given by just the canonical bundle where I remove the zero section of it. So this is a Calabi cone. Okay, here's my notation for the canonical bundle. And okay, and I will assume that the anti-canonical bundle so I denote it with a minus here, is the power of some ample line bundle. Okay, I'll very ample. Okay, so we're in the setting of the Calabi cone, so it could fit in this statement, and so when we rewrite this statement for this particular example, we have the following statement. Every nowhere vanishing section of this bundle so the 1-0 form taking value in the second power of L produce a Gaussian structure on Y. okay? So basically the twist form assumption here is translated here in this section, in this statement. This is the link between the two. Okay, and so now I'd like to give an example of that. So a natural example to consider is the case of Y being a complex projective space. And for this assumption to work, I'm gonna have to take some weird power of the complex projective space. So namely, I take the CP4n-1. Then we all know that the anti-canonical bundle can be written as follows. Okay, and this is my L. And so to make this theorem work, I need a nowhere vanishing section of this thing. So in this setup, it's just I need a nowhere blah 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 section of this. Okay, and so basically when you push everything back to C4n, it means that you want a 1-0 form which is homogeneous of degree 2n with respect to the diagonal action of C4n, okay? And so basically for example, for n equal 1, so in the case of CP3, I was able to prove that we have a whole family of such section. Family. That gives me SU3 structures on CP3. And even better, there is a subfamily of this family, which actually produce LT structures on CP3. And I'd like to make a comment on this because so we might think that this theorem is somehow Taylor reduction, but it is not, because with this twist form condition, I'm actually trying to kill the integrability. So the LT structure I get on CPU3 is not the Fubini study one, obviously. And even weird it's even weird that the Riemannian metric I get with this LT structure is the usual one, as we all know for Fubini study. But the two form and the complex structures are different. And a final word to say that this theorem is a generalization of a construction made by the physicists Larford, Lust, and Simkis. Was in 2010, where they explicitly give a construction in coordinates for toric 6-dimensional manifolds. And so this generalizes the construction in a more abstract way, and that would be all for me. Thank you.
Oh, yeah. Your Taylor quotient gets a natural complex structure.
Yeah.
You don't say how it gets modified by the twist. You're keeping the same complex structure?
No, the complex structure on the quotient is really given by this form, actually. Because when you have a non-zero form like that, the complex structure is really determined by this form. And so it's not the complex structure you could get by Kähler reduction. That's the point of this theorem.
Other questions?
Mr. Can you explain a little bit why you need L to the power 4? Thank you.
Yeah, it's because actually for these things to work out, we need, I use the code-around by adding theorem. And so I really need some twist form to prove this theorem. And basically the twist form I know are on C4, which are of degree 4. And so that's why it works. And I really need this index here for just to make it work.
Yeah, in your second theorem, when you said that like a nowhere vanishing section defines an SUN structure, how does that work? So do you get some omega out of the section? And if so, how?
Yeah, because how does it work? It's basically you apply this theorem where X is my Calabi-Yau cone. Okay, and you have natural moment map, which is like Evelyn talked yesterday about. We have this R function, okay, which is the square norm of the Hermitian matrix on the Calabi-Yau cone, and you look at this gives you a momentum map, and you look at the level set 1, and it's gonna give you back the Y actually. Okay, so the Y over there is the same Y here, and the X should be thought as the Calabi-Yau cone.
So for n is equal to 2 and 3, are there some particularly nice conditions that allow an SUN structure to exist?
Yeah, there are topological obstruction. For example, if you have such a form, it means that the first n class must vanish. Okay, but if you don't know at the beginning there's no SUN structure, you look at for example, for CP3, you look at the usual Fabonista complex structure, and you know that it's C1, his first n class is 4, so which is even. And so topological obstruction is that for any complex structure, the first n class must be even. It's a necessary condition. Yeah.
That's good. So in your first theorem, am I right that even in this non-integrable setting that X cannot be compact?
Here? Yeah, it cannot be non-compact, yeah.
Sorry, could you say that again? It cannot be non-compact?
Yeah. It cannot be, it can't be non-compact, yes.
But it must be non-compact, I guess, is my question.
Yes, you're right. Yeah.
Okay, thanks.
Then I was, yeah.
No more questions? Okay, let's thank Quentin again.